Hello everyone. So welcome to this short video. So in this video, I will quickly explain the solutions of the three clusters that I have taken post midsem. So it was not possible for me to complete evaluating all the answer script of this class three clusters, but since I'm getting some mail that I should at least share the solution such that you'll get an idea that how to answer in NSEM. So let us quickly discuss the possible solution of this class test. So this is the first class test. So if I check the questions of first class test post midsem, so this is the question number one. So this is a very simple question. So here what I asked is, you have as just you have a array of 800 crosses. This is a 2D array, okay, and you need to fetch this all the elements from this array. You can see the program here. So in this, if you see, observe properly this program, every element here of this array you need to fetch just once in the processor, and you will perform, you will just multiply it with 2, and then again you are storing it in the same location, right? So it is a scanning application. You are scanning the all the elements of C only once. You are not requesting one application multiple times here. Okay, so now again and one more point is block size is 64 bytes, right? So if block size is 64 byte, then in one block, suppose this is the block, you can store four elements, right? So if this is C00, then C01, C02, and C03 will fetch at the same time. So when you are fetching B1, so if you see the last two lines, if j equal to 0, then if when you're this j equal to 0, then you need these two elements also. So these two elements will be already there in the cache, because when there will be miss for C00, you will go to main memory and fetch the entire B1, right? So the last two line for this, if j equal to 0 wala, this these two lines will not create any extra miss here. So because this will be always hit in the cache. So you can also assume that the last lines are not there, means if j equal to 0 and this if statement is not there, you can also assume like this, because this will not create any extra misses. So let us just concentrate on this line, Cij equal to 2 into Cij. So in this line, how many compulsory misses will be there? So compulsory misses will be how many, then we have to calculate how many elements are there. 8 into 8 means 6400 elements are there in the array C, right? So if there are 6400 elements, then in one block there are four elements, so there will be 1600 blocks are there, right? If there are 1600 blocks are there, then every block you have to fetch in the cache. So the compulsory misses will be 1600. So the answer of A here, total compulsory miss is 1600. Then the next is total conflict miss. It is 0, because it is a fully associative cache, right? And then the third one is capacity miss. Capacity miss. So what do you understand by capacity miss is when your cache is full. Suppose this is my cache, this is my entire cache, and it is full now. And now if I want to fetch a new block, then I have to select one block first, then you have to remove it, and in this place we have to place the new block, right? So this is called capacity miss. So here you can see that all the 16 all the blocks here you are fetching only once, right? So the total capacity compulsory miss here was 1600. So what will be the capacity miss? So some of you may write that, sir, capacity miss is 0. Why? Because all the misses are compulsory miss. Every miss is new miss. So I'll accept this logic also, that if someone has written the answer of CS0, that there is no capacity miss because all are compulsory miss, I'll consider it. But another point is like this: a particular miss we can consider both as compulsory as well as capacity, right? Because if there is a miss and miss is happening first time, then this is a compulsory miss, obviously. But while when this miss happens at that time, if the cache is full, then you can also consider that as a capacity miss, right? So in second logic, how many capacity misses will be there? The cache size is 1 KB, right? So if the cache size is 1 KB, how many blocks it can store? It can store 64 blocks. Why? Because the block size is 16, right? So 16 into 64 is 1 KB. So if this is the cache, then first 64 blocks, once the first 64 blocks are fetched, then cache is full. So after the 64 blocks, every new block that you will face, that you fetch, for the placing that block you have to remove something from the cache, right? So the answer of another answer of C will be 1600 minus 64 blocks. Okay, so this is the answer. First here, this is 1600 B, 0. C, there are two options, either 0, then also I'll consider it correct. And if someone has written 1600 minus 64 blocks, then also I'll consider it as correct. Okay, so this is question number one. Question number two is very straightforward again, because here also we are assuming that the both the array A and B are stored in row major order. And if both the arrays are stored in row major order, then I think the option A is better, because if we go with option B, then you need a column measure order storage of A is of the array C, because you can manually check also that this one, that is the option B, will receive more misses in the cache. So here the option A is better. So, and question three is related with banks of DRAM. So, though it is not related to the ANSEM, but here, because as I said, DRAM concept will not be there in ANSEM, but still I'll quickly explain it. Since you have multiple banks, right? So, when you have multiple banks like this, right, you have multiple banks in the chip. There are three banks in a chip. So, the each bank, this internal activation and all, those activation and all these operation can be performed in parallel in all the three banks, because they have their independent row buffers and all. Only thing is, once the data is ready and you want to move the data out from the outside the chip, in that case you are sharing the bus. So in that sharing the bus, it is fine. But except this, there are other works internal to each bank, is it can be performed in parallel, and that's why bank is giving benefits. Okay, the fourth question is why we need each state in Messi CMP, right? So the answer is, even if you have, suppose you have, this is the condition that you have two cores C1 and C2, and this is the shared LLC, this is L2 cache. But it has been found that maximum time when a core is requesting for a block, even it is a multi-threaded application, when a suppose code C1 is requesting for a block, most of the time it has been found that only C1 will access it, other core will not access, and most of the time. So in that case, it's been found that most of the time when a core is requesting for a block, the block becomes a private block for this C1, right? So in that case, it is better to directly give exclusive permission to C1, because in future if the C1 want to modify that block, then it no need to send a upgrade request back here if you directly give an exclusive permission. So that's why the e state is important. This is one law, one point. Another point is also there, that is called silent eviction. So but at least if you have written the first point, then I think I'll consider it is correct, and I think I have explained all this point in class also. So if you see my recorded lecture, you will find the solutions also. Why way partitioning technique in UCP? So see, the here I have discussed that way partitioning I've discussed in class, and I said that similarly, instead of way, if I want to partition the sets, then what will be the disadvantage? So here the question is, if you have multiple sets like these, suppose there are four sets here, and you say then no, this set, first two set are for application one, and second last two set are for application two. So in this case, the major challenge will be set remapping, because we if we when we partition it in terms of we, suppose these are the sets again, and this was the we, then I said then no, here I'll partition, and this is for A1 and this is for A2, then it means that we are not changing the set mapping. If a block is mapping in set number one, the block will still map in set number one, only we are restricting the number of ways, right? But it is not happening if we go for set partitioning. If we go for set partitioning, then you need to change the set index mapping, because in that case all the application, no block from application A should map in this last two sets, right? So in that case, sat mapping is will be a major challenge. And if you go for sat mapping, then if you want to dynamically change sat mapping, suppose this is the current state, after some time, if A1 need three states, now after some time, all this partition will be go to A1, and this is for A2. So here now in this state, maybe the blocks of A2s are there, so all these blocks need to be may need to be migrated to, or maybe shifted from this set and all. So there will be a lot of overhead here. So this is the major challenge if we want to go with set based partitioning. Whereas here set based partitionings are also practical. People are doing research in this area also, because set based partitioning is safe in terms of side channel and covert channel attack. Okay, so I think the solutions for class test one is done. So let us discuss with the second class test now. Second class test is here. Okay, so in second class test, the first question was Let me discuss the first question here. Okay, so the first question was there are two cores, right? C1 and C2. Both the core has their private L1 cache and there is a shared L2 cache. C1 is running a scanning application, right, and it is running a cache friendly application, right? So the question was that normally we know that the srrip this replacement policy is scan resistant. It is a scan application cannot flush the entire cache here. So I the question was write a trace such that it cannot handle scan application, and I say that when you are writing a trace like this a1 a2, only concentrate on one set. You no need to think about the other set. Maybe there are multiple sets here. Only concentrate on one set, and I think set, I assume that it is a four-way set associative, right? If I go here, let me check. I said it's a four-way set associative LLC, right? Four-way set associative LLC. So suppose if it's a C2 is cache friendly application, then maybe the trace will be like this: B1, B2, B3, B4. Suppose, and then again B4, B3, B2, B1, and maybe it is repeating. So this is a cache friendly application here. The blocks are accessing repeatedly and it is respecting both principal of locality, temporal locality as well as spatial locality, right? But I said the C1 is running a scanning application. So suppose here, somewhere here, if there is scanning application suddenly start right A1, A2, A3, A4, A5, A6, A16 kind of thing. There is a long scanning application here. Then that scanning application, if the underlying replacement policy is LRU, that it can flush the entire set. Again, I'm saying that we are only concentrating on one set. So all the information that is stored here for B1, that is B1s are related with C2, right? I said here this is A1, A2 are for C1, and B1, B2, B3 are for C2. Okay, so here if if there is a suddenly a scanning application comes from C1, then the entire set in the last level cache will be flushed, right? So this will create lot of misses in C2. So as per the claim of SRRIP that this, if there is a scan application, then scan application cannot completely remove everything from the cache. So if we go to the paper, I think this example I have explained in class C. Here, it is the opposite one. Here, A1, A2, A2. So here, A1 is a cache friendly application. A1 is a cache friendly application. Sorry, A is a cache friendly application here, and B here is a scanning application. So you can see that this scanning application can flash everything in LRU. But if we go it in SRRIP here, you can there is two hits. So it means that the scanning application, that is B1, B2, B3, B4, cannot remove everything from the SRRIP. So that was their property, right? So I said that no, write a trace, this type of trace like A1, A2, A3, write a trace in such a way that these two hits is not possible, right? That the question was write a trace in such a way that the scan application can flush the cache even it is SRRIP. So this is the question. So if the answer is also very simple, if you read the paper or if you observe my lecture properly, so there was a point I said that this SRRIP is scan resistant, provided the value of this M that they are saying, that RRPV value, right? If you go here, then I say the RRPV value is 0 to 3. So this RRPV value must be large enough to handle the scan. So here the RRPV value 0 to 3 was large enough to handle the B1, B2, B3, B4. This this scan. But if the scan was like B1, B2, B3, B4, B5, B6 up to B16, then that scan trace is not possible to handle by this RRPB. You can check here also. The same example you can take and you can check here. Then instead of using here B1, B2, B3, B4, use some more here like B5, B6, B7, and B8, and then you can check. Then you will not face this type of hits here because that scan is large enough for RRPB value 0 to 3. That is not enough. So in that case you need a larger RRPB value, and these concepts are written in this paper. So here it's the answer here. You just need to write a trace like this, that okay, this is a cache friendly application running b1 b2 b4, but in place somewhere if there is a scanning application like this, a1 a2 a3. So if you write this also, that this same application b1 b2 b3 b4 b4, and after this if you write a scanning application like this, and then again b3 b4 bn b1, and then there is a n, then this is a trace like this. So in for this trace, for this particular trace, srip you cannot handle it. Okay, so that's it. Okay, for question 1. If we go to question 2, then question 2 is saying about bip and llc. So if there is a bip and lru, so what is called bip first? If you remember, bip is a insertion policy, right? Bip, just 1 minute. So if it is bip, then sometime it's with high probability it insert in lru position, and with low probability it insert in mru position, right? But if we go here, I already mentioned that the bip that I am using, assume that bip insert every third block in mru position. So means first second will be here, first second block will be here, third block will be here, then again fourth and fifth block will be in LRU position, and sixth block will be again in MRU position. In this way, BIP is storing the BIP that I'm using here, and LRU we already know. So now the question is, you have to write a trace in such a way that the will give you more misses as compared to LRU. So how can you design the miss? So here, as I said, though I said that the cache configuration is same as question 1, but you no need to consider that the core 1 is using a scanning application here for question 2. So now if I write a trace like this, suppose a1, okay, a1 a2 a3, and then b1 b2 b3, and then again a1 a2, then a1 a2, then a4, then again b1 b2, then b4, then again a1 a2 a5, then b1 b2 b5, like this. If I write a trace like this, and you can observe here these elements a3 b3, then a4 b4 a5 b5, these blocks are accessing only once. They We are not repeating this block, but a1 a2 b1 b2 they are repeating. Okay, so here if you use bip in this trace, then what will happen, that every third element it will put in mru. So what it will do, a1 a2, these two blocks it will place in lru position, and the a3 will be placed in mru position, right? But this a3 is useless. It will placing it in lru position means it only create dead blocks, right? So when b1 and b2 will come, then it may be possible that these two will be evicted from the cache, right? So in that case it will increase the number of misses. But if we go with lru, then if it is like a1 a2 a3 b1 is there, so in that case maybe when the lru position, if you maybe you will remove a1, that is fine, but still the lru will give you better performance. So maybe this type of I'm not giving exact solution, but this type of trace is enough, that you have to think in this direction, that when bip will give you more misses. And this is a kind of an example. See here, this every third element that in the trace is not repeating again. And so what bip will give, this bip will give this third element, it will put in an mru, and it will create it will become a dead block there. But in lru it's not like this. So you can write as this type of trace also, and that's why these are the two traces that I was asking in question 1 and question 2. And in question 3, this is an interesting question. So in question 3, what I said, that you have since you know chemsim, so now I said using chemsim, suppose this is your last level cache, right? This is your last level cache, and in last level cache replacement policy is dip. So if it is DIP, then DIP means either LRU or BIP, right? So LRU or BIP means sometime in a, if from this interval there will be multiple intervals like this, right? So maybe in this interval it is LRU, in this interval it is BIP, in this interval again it is LRU, right? So but suppose this is the core C1, this is the core C2, they have their own L1 cache. Okay, this is the share L2 cache. So now there is the application running in this core. Suppose C1 is running, an application A1 is running in this core. So now suppose I am the writer of this application. Suppose this is the application A1 is A1.c. I have written it. So as a user of this processor, directly it is not possible to know that at this moment. Suppose this is the time. So at this moment either LRU or BIP is running on LLC. Is not possible to know, right? So now my question was, can you design a trace in such a way that the application, this application can understand that either LRU is at this moment LRU is going on or BIP is going on. So this was the question. So lot of hints given in this question, and the main point here is depends on meet, hit and miss. And I said that assume that this application, since it's a chem sim, so you'll simply send a trace, right? You say because it's chem sim, it's you will run a trace. So when you are running a trace, you have to create a trace in such a way that. And one more point I said that when you are running a trace, so you are here in this core, you are also recording the time, that the time it is taking. Suppose this core will, for this is a trace, suppose A1, A2, A3, A4, this is the trace you are sending from this core. So first core is sending A1 here, then A1 will go down, and then after some time block will receive here. So this core 1 will record the time that is taken to receive A1. Then same way core will also record the time for A2, for A3 and A4. So all the uh, block requests that it is sending to the memories, so it will also record the memory access time for that block. So obviously if this block is a hit in the last level cache, then the time will be less compared to if the block is missed in the last level cache. Suppose the request is going for A1 here in last level cache, it is a hit in last level cache, then maybe the time taken will be 1 nanosecond. But if there is a miss in last level cache, the time will maybe 100 nanosecond, because I have to go to main memory and fetch the block. So these, based on these time gap, okay, now the core can understand, or the application can understand that whether it was a hit or a miss, right? So now what I was expecting, and my question is, I have to understand if it is a LRU or it's a BIP, right? So now we know that LRU is not scan resistance, or it is not thresh resistant, right? So maybe I'll create a threshing application or threshing trace, and I'll run it on C1. And if that threshing trace is giving me more misses, then obviously the replacement policy is L1. And if that tracing trace is giving me less misses, it means that underlying replacement policy is BIP, because it is handling some of the it is handling, partially handling the trash, because we know that BIP can partially handle a trash based scan or trash based application, right? So first thing is the time, right? Based on time, if the time taking to access a block, if the time is high, based on this it can assume that it's a hit or miss. So all these points are written here. You no need to write about the time complexity and all, right? All everything is written here. You just need to write that how it is possible to create a trace based on who is an attacker can find out that okay, it is LRU is going on or BIP is going on. So the answer was straightforward, that you just need to write a thresh based application or threshing trace. And when the threshing trace will run, you just observe the number of misses and number of hits. If the number of misses are more, it means that underlying replacement policy is LRU, because LRU cannot handle trash. And if the underlying policy is BIP, then obviously the number of misses will be less, because BIP can partially handle the number of misses, partially handle thresh application. So that's it. That is the solution for question 3. Okay, so the question 3 is done. Now the last quiz, that is the quiz number 3. So the quiz number 3 is I think also straightforward. So here if we go with the first question, this is the risk free program, and I said that if it is in order execution, so if there is in order execution, then there is no chance of war hazard and wow hazard. There will be only possibility of row hazard, right? So you can easily find out how many row hazards are there. So there is a row hazard in first and second application, because loading a instruction in means load is loading something in x1, and the next instruction is using it. So there is a data dependency between load and add. So there is one row hazard here. Another row hazard is I think in between add and store. So there is a add is updating the value of x2, and store is storing this value in memory. So there is one more data dependency between add and store. So these are the two data dependencies, and one more data dependency is possible between this load and this sub, because this load is loading something in x1 and this sub, so there will be three row hazard possible. in question 1, and 0 war hazard, 0 wow hazard, because this row war and wow hazard are not possible in order execution. But in question 2, I said that if I assume it is out of order execution, then obviously there will be row hazard will be same, but there will be some addition in war hazard and wow hazard in question number 2. So how many war hazard? War hazard means right after read. I think I have explained it in class. So right after read, it means if a upper instruction is reading it, then I have this that read has to complete before writing it by the next instruction. So you can see here. I think this sub is writing in x2, right? So and this store is reading the x2. So this read the store the read of the store instruction must be completed before executing the last instruction sub. So there is a right after reads header between the last two instructions here. Okay, so similarly the right after right hazard is possible here between the second and fourth, or second and last instruction, because both second and last instructions are writing on x2, right? And x2, so it means that the last instruction cannot write x2 before the first instruction, otherwise the store will get wrong value, right? So that's why there is there are three row hazard possible in question 2, one war hazard and one wow hazard possible. So that is the solution of question number 2. So question number 3, solution: what is the advantage of gain cell? Again, it's not in ansem, but the advantage is I think I have already discussed in class that it is faster. Plus another advantage is it will not discharge when we will read something from the gain cell as compared to commodity DRAM cell. Okay, and out of all the non-volatile technologies, why only STT-RAM is considered as possible technology to design LLC? Because this is the only non-volatile memory which we can use, because it is less. Its latency is manageable for last level cache. Other non-volatile memory has very high latency. So those so that's why those memory technologies cannot be used in last level cache. But STT-RAM, the latency overhead is manageable, and it can be used as a cache memory, and that's why every modern day, every last level cache which is designing with non-volatile memory, the technology used is STT-RAM. Okay, what are the two major challenges of using STT-RAM to design last level cache? Two major challenges related to write only. First major challenge is write endurance. If you in STT-RAM, if you write something in the same cell multiple times, then the this cell may damage faster as compared to other cells. So here you have to distribute the write, right? So this is called write endurance problem. This is the first problem. Second problem is the latency. Here the read and write latency are not same like SRAM technology. In STT-RAM, read are fine. Read latency is comparable to the SRAM technology, but the write is write takes more latency as compared to SRAM. So these are the two problem here: write endurance and write latency. Okay, so I think that's it. These are the solutions for quiz 1, quiz 2, and quiz. I can quickly go back again and I can check. These are the solutions for quiz 1. So in quiz 1, total compulsory means 1600. I hope I have explained it. Conflict means there is zero because it's a fully assertive case. Capacity means either you can consider as zero, because or you can also consider it as 1600 minus 64, right? And for question 2, option A is better because the matrix stored is in row order format. If you go with option B, then for loop is changed, so column order matrix is required here for less misses. So option A is better. Question 3 I've already explained. Question 4 I think I've explained already. So question 3 may be important for exam. So here you have to understand why each state is important, because as I said, maximum time when core requests for a block, it has been found that the block may be private only for that core. Other core will not access this block. So if this is the case, then it is better to give exclusive permission directly to this core to the for this block to this core. So what is the advantage here? Because in future, if this core want to write something to that block, then it will not send, and it is not required to send the upgrade request because it has already the exclusive permission. So that is one of the benefit of using messy protocol instead of MSI protocol. And way partitioning, question number 5, I said the problem here is set mapping, right? So if I go to third class test, then as I said here in question number one, there will be no war hazard and wow hazard because it is the in order execution. And when we go to question three, when I assume that consider that this is out of order execution, then row hazard will be same. There will be three row hazard and there will be one war hazard and one wow hazard here in this program, right? And then I think non-volatile memories I have explained also. And if I go to this class test number two, then here I think this was the main confusing part for you, but I think this question, the answer was very straightforward. For first question, you just need to write a long enough scan application such that that scan cannot be resisted by SRRIP application. That's it, because SRRIP, they claim that it can resist scan, but that scan resistance capacity is depend on their RRPB value. So the example that is given here, this example, if the scan B1, B2, B3 is more like B1, B3, B4 up to B8, then that scan cannot resist here by this small RRPV value. Here RRPV value that taken is maximum is 3. So either you need to change RRPV value. So if you see the question, RRPV value is fixed between 0 to 3. So it means since I have fixed RRPV value, so based on this, you can write a long scan application in such a way that it can evict the entire scan. So that was the only requirement, that you should write a long scan application. Okay. And in question two, as I said, you need you have to create a you have to create a trace in such a way that BIP should give less performance, and I have created a trace in this video, right, for this. And question number three was related with cache security, but I think uh, uh, a lot of or the hints required are already given. How to measure cache hit, how to measure cache miss, already everything was given. So the answer here is you need to run a thresh based thrashing trace in core 1 or core 2, and just need to find out and count the number of misses. If the number of misses are high, it means LRU is running, and the number of misses are low, that means BIP is running. So these are the solutions. So I hope the points are clear. I am evaluating your answer script, but answer script of class test is not possible to finish by tomorrow. So you will see your all the marks of class test as well as end sem together. Okay, so thank you for listening this video. I'm stopping it here.